This video is all about improving your ability to solve interview questions involving binary trees and depth-first search. We'll learn by looking at a few example problems. For each problem, I'll first highlight the underlying concept at play and then show how those concepts relate to the implementation. By the end of this video, you'll be much more clear about how to implement solutions to these types of problems. We're going to start by learning how to extend depth-first search. We'll do so by looking at depth-first search in its most basic form and visualizing how that function executes over a binary tree. Execution begins with the first call to depth-first search on the root of the tree. Since node is not none, we reach the first recursive call to depth-first search on the root's left child. To represent this call, we add a call to the call stack and begin executing the body of the recursive call. In that recursive call, we reach another recursive call to depth-first search, which we add to the call stack and begin executing. The value of node is none here, so we reach our first return statement. In this basic form of depth-first search, the value of the return statement is none. But for now, we're less concerned with what this value is and more concerned with where it goes. So where does this value go? It goes to the previous call in the call stack, which is associated with the current node's parent. So visually, we can think of the return statement as containing a value that each node sends up to its parent. The parent receives that value and stores it in a variable called left. It then initiates a recursive call for its right child, and the right child eventually sends a value back. Having now received values for both its left and right children, the parent node can now use those two values to send a value up to its parent via the return statement. This process continues through the tree, with nodes at higher levels initiating recursive calls downwards to their children until the leaf nodes are reached. Those recursive calls eventually return values that each node can then use to return a value back up to its parent. This process makes its way back up to the root of the tree, and when it reaches the root of the tree, we have enough information to solve the final answer to our problem. Let's now apply this process to an example problem by writing a function to find the sum of all nodes in a tree. And because we are extending depth-first search, we're going to find that sum by creating a chain of values that each node receives from its children below and then uses to return a value up to its parent. The sum of the nodes in a tree is the sum of the nodes in the tree's left subtree plus the sum of the nodes in the tree's right subtree plus the value of the root node. This also applies to every subtree in our tree. For example, we can find the sum of the root's right subtree by receiving the sum of its left subtree from its left child and the sum of its right subtree from its right child, and then adding those two values to the value of its own node, which can then be returned to the root. When we formulate the problem like this, in terms of the value that each node receives from its children below, and two, how it uses those values to return an answer to its parent, the body of the function practically writes itself. We start with the base case. When node is none, our subtree is empty. The sum of nodes in an empty tree is 0, which we can return directly. Next, we receive the sum of our left and right subtrees via recursive calls to tree sum on node.left and node.right. Notice we don't have to specify how to get these values. We can simply assume that the recursive calls will return them correctly when writing our implementation. Finally, in our return statement, we add those two values along with the value of our node to return the sum of our subtree to our parent. We're now going to visualize the execution of this function. Execution begins at the root of our tree. Since node is not none, we reach the first recursive call to tree sum on node.left. This recursive call represents the sum of the root's left subtree. When it eventually returns, that sum will be stored in the variable called left. We add the recursive call to the call stack and begin executing. Node is not none here, so we reach another recursive call, which we add to the call stack and begin executing. Here, node is none, so we reach our first base case and return statement, which returns a 0 to its parent. The parent, having just received the sum of its left subtree and stored that value in the variable left, moves on to the next recursive call, which represents the sum of its right subtree. This is another base case which returns 0, which the parent receives as the sum of its right subtree and stores in a variable called right. Now, having received those two values from its children, it adds them to the value of its own node and returns that value 3 to its parent. The root now has a sum of its entire left subtree, and it can move on to initiating the recursive call, which eventually returns the sum of its right subtree. This recursive call initiates its own chain of recursive calls, and from the root's perspective, we can think of the sum of its right subtree as being stored in this chain. The chain contains the exact details of how these sums are obtained, which allows us to just assume that we have those values when writing our implementation. As long as that chain is initiated, we trust the way that we extended depth-first search to receive and return values at each node to eventually return the right answer. And so when that chain returns with 21, we can take that value, Add it to the sum of the root's left subtree, which is 3, and add the value of the root node to get the final answer, which is 29. The next question we're going to look at illustrates when to introduce a variable that is accessible by every single recursive call. We're looking for the diameter of a binary tree. The diameter of a binary tree is the longest path between any two nodes in the tree. This longest path doesn't need to pass through the root. For example, in the following tree, the diameter passes through the root's right child. We define length to be the number of edges in that longest path, which is 6 in this case. We want to solve this problem by extending depth-first search. At each node, we want to find the length of the longest path going through it. We will calculate that length using values received from the node's children. Each node will also return a value to its parent that the parent can use to calculate its longest path. By the end of the depth-first search, the diameter of the tree will be the largest of the longest paths we found at each node. Here's a process I like to use in order to determine what each node should be receiving and returning. I anchor myself at a non-root, non-leaf node in the tree, as these nodes are positioned to both receive values from their children below and return a value up to its parent. From here, we can draw the length of the longest path going through that node and ask, what information do we need from our left and right children to find this path? We can observe that the longest path going through our node contains the length of the longest path starting at both our left and right children. So, if we were to receive those two values, we can calculate our longest path by adding those two values together, plus 1 for each edge that exists between our left and right children. Finally, we calculate the length of the longest path starting at our node, which is 1 plus the larger of the two values returned by our children, and return that value to our parent so that it can calculate its longest path. Notice that although we calculated the longest path going through our node, that value isn't the same as the one that gets returned to our parent. Once we've determined what each node should receive from its children and return up to its parent, the implementation of the solution is straightforward. We've clearly defined what each node should return, which is the longest path starting at that node. This definition informs the base case. The longest path starting from both the empty node and a node with no children are 0, which we can return directly. The next step is to assume we've received values from our left and right children. Using those two values, we can compute the length of the longest path going through our node and save it in a variable max, where the value of max is left plus right plus 1 for each edge that exists between our left and right children. Finally, each call will return the larger value between left and right plus 1, which represents the length of the longest path starting at our node. Let's now take a closer look at the execution of our function by zooming into the recursive call made on the right child of the tree's root. We'll start right after we've received answers from our left and right children. Execution continues by creating the variable max to compute the number of edges in the longest path going through our node. But since our return statement actually returns the length of the longest path starting at our node, the value of max is lost when our function completes. This presents a problem because the value that we need to return at the end of our function is the largest of the max values calculated at each node. We'll create another variable called count to represent this largest value, initialized to 0. This variable needs to be accessible by each recursive call, so we'll make it global. Each node, after computing max, compares max to the value of count and updates count if max is greater. So now, whenever a recursive call updates count, that update is made visible to every single recursive call which is still active. And when our function completes its execution, the final diameter of the tree will be stored in the value count. The next question we're going to look at asks us to determine if a binary tree is valid. This example illustrates when it is necessary to introduce a helper function to help with the recursion. A binary search tree rooted at a given node is a valid binary search tree if 1. The value of that node falls within the acceptable range of values, and 2. Both its left and right subtrees are valid binary search trees. The second requirement hints at what each node should return during the process of receiving and returning during depth-first search. Each node should receive the answer for whether its left and right subtrees are valid binary search trees via recursive calls. If both of those are true and the node's value falls within the acceptable range of values, then the node can return true to its parent. So now let's look at the first requirement, that the value of each node should fall within the acceptable range of values. A node's acceptable range is determined by both the value and the acceptable range of that node's parent. We're going to see how that works by filling in values such that this tree is a valid binary search tree. The root node of a binary search tree can have any value. So let's just say that value is 5. By the definition of a binary search tree, every node in the root's left subtree must be less than the root. So when we move onto the root's left child, we know that this value must be less than 5. So we choose 3. The same applies to the acceptable range of node 3's left child. Its value must be less than 3. So we'll choose 1. The right child of node 3 must have a value greater than 3, but since this node is also in the root's left subtree, it also must be less than 5. We'll choose 4. When we're thinking about the process of receiving and returning during depth-first search, we're concerned with values that make their way up the tree. But here, to determine each node's acceptable range, parent nodes must pass information down to its children. Whenever we need information to flow down from parent to child nodes, we require a helper function to perform the recursion. This helper function will introduce extra parameters that parent nodes can use to pass information down to their children when making recursive calls. In our validate binary search tree example, we'll introduce 2 extra parameters to our helper function, representing the min and max of each node's acceptable range. When a node makes a recursive call on its left child, it updates the max of the left child range to be the node's value, while min remains the same. When making a recursive call on a node's right child, the value of the parent node becomes the min of the right child's range, while max remains the same. With that mechanism in place, let's go ahead with our implementation. We want to introduce a helper function to perform our recursion with 2 extra parameters, min and max. As we saw in the receive and return breakdown, each call to our function returns a boolean indicating if the subtree rooted at the given node is a valid binary search tree. This informs our base case. The empty tree is a valid binary search tree, so it returns true. Next, we check if the node's value falls within the acceptable range. If not, we know our binary search tree is invalid already, and we can return false without having to recurse any further down. Then, we receive if both our left and right subtrees are valid binary search trees by making recursive calls to our left and right children, updating the min and max of the parameters in those calls accordingly. If our left subtree is not a valid binary search tree, we can return false before having to recurse down to our right subtree. Finally, our function returns true if both left and right are true or false otherwise. Our main function will then initiate the first call to the helper function with the acceptable range for the root, which is -infinity to infinity. We'll now visualize how this function executes on an invalid binary tree to see what it looks like to return early without having to recurse over the entire tree. In our first call to the helper function, node is not none, and 10 falls within the range of -infinity to infinity, which brings us to the first recursive call. This is a recursive call to a left child, so the value of min for this recursive call remains the same, while max becomes the value of the current node, which is 10. In this recursive call, the value of the node falls between the acceptable range of -infinity to 10, so we reach our next recursive call. This is also a call to a left child, so the value of min remains the same, while max becomes the value of the current node, which is 7. In this recursive call, the value of the node is greater than the minimum of the acceptable range, so we return false. Notice how we return false before making any further recursive calls to our left or right children. The previous recursive call receives this value false in the variable left, indicating that the left subtree of the current node is not a valid binary search tree. This violation allows the current node to return false to its parent without having to make a further recursive call to its right child. The previous recursive call receives this value false in the variable left, indicating that the root's entire left subtree is not a valid binary search tree. The root can now return false to the main function, and we're finished without having to recurse over any of the root's right subtree. Let's now recap everything we learned. We first learned how extending depth-first search involves establishing a process of receiving and returning. Each node receives answers to some portion of the problem from its left and right subtrees. It then uses those values to return an answer up to its parent. To help determine what each node should receive and return, we anchor ourselves at a non-leaf, non-root node in the tree and ask, what do we need to know from our left and right subtrees in order to solve our problem? When the solution to the problem differs from the value that each recursive call will return, we need to make sure the variable holding the solution is accessible by each recursive call. One way to do that is by introducing a global variable. And when the problem requires passing information down from parent to child nodes, we do so by introducing a helper function with extra parameters to help us recurse. Implementing any recursive solution that extends depth-first search can be done in 4 parts. First, we fill in the base case, which comes naturally from what we determined that each recursive call will return. Second, we receive answers from our left and right subtrees via recursive calls. Third, the compute step involves either using the answers received from step 2 or any extra parameters introduced by the helper function. Finally, we use those answers received from step 2 to return an answer to our parent. And that's it for this video. Happy implementing. Hope this helps.